Hello. In this video we're going to talk about Schrödinger's cat, and remarkably I'm actually going to be able to show you an experimental implementation of it, but don't worry, no cat is going to be hurt, and Jeffrey the dog is going to be fine. No animals will be involved. I'll be the cat. So Schrödinger's cat tells us about what's called the measurement problem in quantum mechanics, or it's a particular example of it. So we know that we can take a system and we can create a quantum superposition of quantum states. So, for example, we could take a two-level system. We could describe the system by the state psi, which is equal to, for example, we could call it spin up and spin down, and we could create an equally weighted superposition of up and down. Or we could call the two states 0 and 1. And we could say that we want state 0 plus 1 over root 2. The root 2 here is just for normalization. And this would be an equally weighted superposition of those two states. So spin's a good example. We can create a superposition of spin up and spin down quite straightforwardly by measuring in a perpendicular direction, for example. So we might think that this is this quantum superposition, which we don't see on everyday scales. Maybe it's just some quirk of small systems, and the fact that we don't see it is just, no more weird than the fact that we don't experience the world on the scale of electrons, say. Schrödinger's paradox shows us that it's much more of a problem than that, and actually it is a big problem for philosophy and physics on everyday scales. So the basic idea of the essence of the paradox was actually come up with by Einstein in letters to Schrödinger, but Schrödinger made one key development, which is, I think, why it's become such an important idea more widely than physics, and that is that Schrödinger changed the story into involving a cat. So cats are quite popular, and I think this has probably helped with the popularity of the paradox. So here's a retelling of Schrödinger's paradox. So you take some measurement device which can measure a two-level system, like a spin a half, so it could be this, and you prepare the state in a quantum superposition of two states. Let's say they're equal probability, like this, or you can call them 0 and 1. And you set a timer on your measurement device, so it's going to make its measurement after 1 minute, say. Now, you rig up the device to a vial of poison, so that if the device measures spin up, it's going to break the vial open and release the poison. And if it measures spin down, it's not going to do that. Now you take the whole setup and you stick it in a box, and then you go and get a cat and you put a cat in the box, and you put a lid on the box. Now the measurement's going to be made after 1 minute. You wait for 2 minutes, and then you take the lid off the box. And just as usual, as doing this experiment is, you find either a dead cat and a measurement device saying that it measured spin up, or you find an alive cat and a measurement device saying it measured spin down. Okay, so that's pretty unethical. What happened before the 2 minutes were up, though? So in the first minute, presumably the cat is alive and happy enough, as happy as a cat can be when it's been shut in a box. But in the second minute, the measurement device has made its measurement, and it has a 50% chance of measuring up or down. And so it has a 50% chance of breaking the vial or not, and the cat has a 50% chance of being dead or alive. Now, we don't know which of those two things it is, so in that second minute, we're still only able to write down a quantum state for the cat, which describes the system as an equally weighted superposition of the two outcomes. And so then we need to describe the state of the cat as an equally weighted quantum superposition of both dead and alive in that second minute. And that's Schrödinger's paradox. That's an absurd statement, and Schrödinger made the statement to try and show that something was going wrong in our logic here. But these days a lot of people accept that that is a fact of reality, that you can have quantum superpositions of large-scale objects. Now, I think, so it's important to note that this isn't the same as taking a coin and tossing it and catching it and slapping it on your hand and saying, I don't know whether it's heads or tails, so I'm going to describe that by a 50% probability for each. Because in that case, it really is heads or tails. I just don't know which one it is. And there's a fundamental difference between that and the making an equally weighted quantum superposition. And I think the easiest way to see that there's a difference is that we can make use of quantum superpositions, whereas we can't make use of the fact that we don't know what the coin is heads or tails. And an easy way to see that we can make use of it is by putting it to use in a quantum computer. So a quantum computer can carry out certain calculations exponentially faster than any classical computer ever could. Okay, so they make use of two key properties of quantum mechanics. One is superpositions, and the other is what's called quantum entanglement. So in the present setting, actually, entanglement isn't that mysterious. It was actually come up with by Schrödinger. The phrase was come up with in German in these letters to Einstein regarding Schrödinger's cat. And it's actually, in this case, it's just a simple statement of conditional probabilities, effectively. So if we think what's happening in that box, the spin is in a superposition of being a spin up and spin down. Now the measurement device, after it's made its measurement, but before we've looked, either measures spin up or spin down. But of course, what it measures is conditional on what the state is. So if the measurement device finds spin up, that means that the spin must be spin up. Okay, it's conditional on that. If the spin is measured to be spin up, so if the spin is spin up, then it's measured to be spin up. If it's spin down, it's measured to be spin down. Okay, so it's a form of conditional probability, but in quantum mechanics, of course, we use amplitudes rather than probabilities, and then we use the Born rule to get the actual probabilities. So in this case, entanglement is no weirder than saying that if the device has measured spin up, that means that it must be the case that the spin is spin up, and so on. And so that's a form of entanglement. Schrödinger says that the measurement device has become entangled with the quantum system, and that's how we've kind of scaled up this superposition to a large scale thing like the cat. Because then if the measurement device measures spin up, it breaks the vial, it kills the cat, and so then you have you've entangled the state of the cat with the state of the measurement device and with the state of the spin half particle. So the fact that we can use quantum computers to do this kind of thing now means that I can do this experiment in my house. And the reason for this is that various companies which have built quantum computers have provided free access to them online. And so you can just sign up for an account and you can just use a quantum computer. Now, you can only use a few qubits at the moment. So a qubit is a quantum bit. A bit of information would be either 0 or 1, hence the nomenclature 0 and 1 here. A qubit, a quantum bit, is also either 0 or 1, but it can also be a quantum superposition of 0 and 1. For example, this equally weighted superposition we just considered, but it can be any other superposition. So in quantum computing, you can write quantum algorithms mainly for testing your approaches to quantum computing. But we can use one. I can log into one now. So I'm going to do that in a second. I'll use one of IBM's quantum computers in New York. And what we can do is create this superposition, and then we can measure it and say, are you in state 0 or in state 1? And there'll be a 50% probability for it giving either of the outcomes. Okay, so let me just show you the setup. I'll switch over to showing you my screen. So this is the IBM quantum experience, and I'm logged into the quantum computer in New York. And here is, so you can see, here's the code you write. There's a Python interface for it. It's pretty straightforward. But actually, the way you write quantum algorithms tends to be in this much simpler method using diagrams. So you have various tracks running along where you initialize qubits and then you perform different operations on them, what are called quantum gates. And they can transform qubits and they can entangle them, disentangle them, this kind of thing. So all I want to do is create this superposition I just showed you. And so the convention is that you start off with a load of qubits prepared in the state 0. So this could be spin down, for example, if they were using spins. Actually, I think they're using the polarizations of light in these experimental setups. And so we need to act some kind of operation that turns our state 0 into an equally weighted superposition of state 0 plus state 1 over root 2. Now the operation that does that is given the symbol H, and it's what's called a Hadamard Gate. So it's not a Hamiltonian, it's just someone else's name that began with H. So a Hadamard will switch our state 0 to an equally weighted superposition of 0 and 1. And then this symbol here is a measurement symbol, and what it does is it takes our quantum bit, our qubit, and it's going to project it down into a classical bit. Because once the measurement's been made, we've got a classical outcome read out. So it's going to measure the state and give a readout. So you can set it running. I can go to jobs over here. I've actually run it already, but I can rerun it for you. You can run it many times, and that's usually the use of this, but I'm just going to run it once, just because I want to get one outcome or the other. Now, to be Schrödinger's cat, what I want to do is I'm going to do something different depending on the outcome of this quantum measurement. So let's say if we measure 0, I'll go and sit on the left side of my sofa, or actually I'll sit on the right side of the sofa over there. And if it measures 1, I'll go and sit on the left side of the sofa. Okay, so we can set our job going. So we set it up, logged into there, so let's run it. Okay, so it's sent off to New York, and we're queued, and we can expect to wait about an hour for that to go through. So I'll fast forward on the video. So the quantum computer measured the state to be in state 0, and so I came and sat over here on the right of the sofa. If it had measured 1, I would have been sat over there where Jeffrey is on the left. So after the computer had made its measurement, and after I'd looked at that measurement, but before you'd look to see which of the two things I did, then you had to assign an equally weighted probability to me being here or there. And since you're ultimately describing a quantum state, you actually had to assign an equally weighted quantum superposition of amplitudes of me being here and me being there. So how we explain this situation is a matter of philosophical interpretation. We describe the different possible explanations as interpretations of quantum mechanics rather than theories of quantum mechanics, because they're not strictly theories in the scientific sense, since they all make the same testable predictions. They don't make different testable predictions, because to do so they'd have to disagree with the mathematics of quantum mechanics, which are extremely well tested against reality. There are some cases where theories truly diverge from the predictions of quantum mechanics, and we'll take a look at some of those in a second. So, to look at some possible options, let's return to the worked example area. So, probably the most mainstream interpretation of quantum mechanics is what's called the Copenhagen Interpretation, developed in Copenhagen by people such as Niels Bohr and Werner Heisenberg. So in the Copenhagen Interpretation, we say that something special does happen when a measurement is made, and that special thing is what's called the collapse of the wave function, a wave function collapse. So when we go from the quantum superposition 0 plus 1 over root 2, let's write that down. So we start in this state. Measurement occurs. And in our case, we found the state 0. So the state of the system really has changed. But this leads to a whole set of philosophical problems. For example, what constitutes a measurement? In the case of the cat, when I've looked into the box to see the cat, I find it either dead or alive. So then that could constitute the measurement, my looking. But why can't the cat collapse the wave function? Why? Surely the cat, which either dies or does not, is a pretty good measurement device. But that would mean that the wave function had collapsed before I opened the box. But similarly, why can't the measurement device itself count as the measurement device? And so the wave function has collapsed before it gets to the cat. At what point does something constitute a measurement? Is it the size of the measurement device? Is it like the number of particles in it? Is it its physical size? The Copenhagen interpretation doesn't really comment on any of these things. A view that often goes along with the Copenhagen interpretation, although isn't necessarily a part of it, is encapsulated in the maxim "shut up and calculate," which says that don't worry about these kinds of questions, just use the maths and it'll make predictions which are extremely well tested, so that's all you need to worry about. Actually, because it's basically the oldest interpretation, or the oldest attempt at interpreting quantum mechanics, it hasn't worried too much. The interpretation hasn't worried too much about trying to answer all possible questions. Later interpretations that came around were developed in distinction to the original Copenhagen interpretation, and so they were often addressing some particular point which it hadn't commented on. So another very mainstream view is the many worlds interpretation. So this says that wave function collapse doesn't occur. Instead, it says what happens is that when the measurement is carried out by the measurement device entangles itself with the quantum state. So remember, in Schrödinger's description of the system, it says that the conditional probability, which in this case is a kind of conditional amplitude for measuring spin up, say, that's conditional on the state actually being state spin up. So we can do it schematically something like this. We can say we start off in this state as before, 0 plus 1 over root 2. But we have a measurement device there which just hasn't made a measurement yet. So let's write a kind of special multiply sign. Actually, this is what's called a tensor product. And there's a measurement device. And what happens when the measurement is made is that this state now becomes a form of conditional probability and really conditional amplitude of the following form. So either we have the state 0 and we measure 0, or we have state 1 and we measure 1. And all of this is still over root 2. So this tensor product denotes, so here we have what's called a product state. You can think of the tensor product much like the usual product. It's just that these things are states, so they're vectors in the complex Hilbert space. And so this is what's called a product state and is not entangled. This cannot be written as a product state. And anything which can't be written as a product state, any sum of states which can't be written as a product state, is what's called an entangled state. And so this is a way of mathematically codifying what Schrödinger had said, that the measurement device becomes entangled with the state of the system. And so in the many worlds interpretation, this is taken quite seriously, and then some mechanism is said to be in operation which causes these two possible outcomes to separate somehow and not talk to each other. Because ultimately you end up, so measure 0 is really, it ends up with you having seen the outcome of measurement 0, which in this case was a dead cat, and measure 1 ends up with you seeing a live cat. And since we don't seem to be in superpositions of seeing dead and alive cats, we must either be in this state or this state. And so the idea is that something causes these two possible outcomes to stop talking to each other at some point. So a common way to explain this is by what's called decoherence. We say that while the quantum particle can be in these quantum superpositions and so on, once you start coupling it to big things, the quantum information starts leaking out into the environment. And while the state is truly still behaving in its quantum manner, it may appear to be classical to any given observer because the quantum properties have effectively leaked out with the leaking of information. It's a little bit like saying, if somebody goes and shouts into the woods and then you go there 5 minutes later, we don't know what they shouted, you weren't there for the shout. In principle, though, you could go around and measure all the different vibrations of the leaves and so on and piece back together what the word was they shouted. But of course, that's never going to actually happen, even though the information might technically be there in the sense that the information is never really lost. It's useless to try and piece it back together. So quantum information can similarly kind of seemingly dissipate to observers while actually being conserved. So the name many worlds comes from a common interpretation of this, that this branch becomes effectively a separate universe to this branch, which then you have this sort of philosophical baggage of explaining where those universes coexist. The idea would be not that they physically separate, but they're sort of in the same place but not talking to each other, so may as well be in different places. Another interpretation, which actually is a scientific theory, is the set of objective collapse theories. So these make different predictions to quantum mechanics, but they do so in such a way as to not disagree with any measurements which have so far been carried out. So in particular, they'll say that something does cause the collapse to physically happen. It doesn't have anything to do with the person measuring it. It's just a matter of coupling to a large device. Large could either mean physically large, perhaps having different effects of gravity on the different ends, or it could mean large in the sense of lots of particles in it. So there are various theories along those lines, and they'll tend to say that the cutoff scale is somewhere, well, it must be somewhere between the quantum scale and our everyday scale, and in fact we've narrowed it down to somewhere in the mesoscopic scale. So as we are able to maintain quantum superpositions on larger and larger systems, we kind of narrow the region in which these objective collapse theories could operate. And in principle, we'll be able to test that full range of theories if we get good enough at our experiments. Okay, so there are some different interpretations of the measurement problem, and as shown clearly by Schrödinger's cat and Schrödinger's paradox. And it's interesting to try and think which you agree with, and perhaps you don't agree with any. Or perhaps you have one that you particularly like. Okay, thank you for your time.